Alright guys, bear with me, I am not used to using microphones, but anyway, good morning everybody. I am Elaine Gospers, I am the project manager for Elk Construction Consultants, and today we'll be talking to you about our progress on the Amazon Industrial Site project. Just to review, we have had some personnel changes. I am still project manager and I'm still transportation lead. However, today with me I have Chris Wang as our water resource engineer. I have Elizabeth Walker with me, who is the environmental engineer 1, and I have Caitlin Frank, who is our environmental engineer 2. We no longer have a structural component to our project. All right, I'm going to just jump right into my transportation component for the project. I did bring with me some sets of plans, only 4, so you guys would like to pass these down. These are a set of 26% plans, so you'll notice on blank pages, and I would also like to note that me and CAD will be working on our professional working relationship because all of the annotations did not print out, and neither did the vertical alignment. Anyway, starting off, I would like to review the scope of work. The scope of work for the transportation component on this project includes a new connector from County Road 19 to County Road 4, including an intersection with the Indiana Toll Road entrance. This intersection will be signalized, and the other intersection at the eastern half of the project will be a stop control at County Road 19, and the design, scope of work for the design also includes any access and parking lots for all facilities, including the warehouse building, which at this point is no longer being developed. However, the parking lot is still going to be designed for future possible use. For the design criteria for this project, for the transportation component, it was using mainly the Indiana Design Manual, but some additional criteria was taken from the AASHTO Green Book, as well as Elkhart County codes and ordinances. The values that you see here were found using the IDM figure 53.8, which uses the volume to classify the road. Some main points here, 12 feet travel lane width has been chosen, and after that, most of this is just criteria that goes into like the cross sections. So this design alignment you can see is just a preliminary sketch. You can see the full design alignments on your sketch, the plans that you have there. The minimum curve radius for this design is 645 feet, and you can see that there are 2 horizontal curves on the alignment, which are both set at exactly 645 feet. This is a sketch of the typical cross section. You can also see on your plans there as well. One thing to note is that there is 12-foot travel lanes with a 2% grade, and different to many designs that you may see is that we are using a concrete up-base top course instead of a asphalt top course. This is to alleviate any pressure that we may have from our design vehicle, which is the WB67, and additionally to have an easier transition from the toll road, which is where the alignment will be coming in, which is also a concrete top course. This is just a sketch to show the intersection details. As you can, again, tell, all of the annotations that were initially provided on the plans are no longer there. Again, me and CAD will be working on a professional relationship. The turning radii are a minimum of 125 feet in all turning movements due to the speed of 45 miles per hour. All inner corners are at 125 feet, but the outer corners may be slightly above that. The storage lengths chosen for this intersection, which is on the toll road entrance, is 50 or 100 feet. This is depending on the turning movement volumes. And the deceleration length is 385 feet, which is due to the 45 mile per hour speed of the road. And the table lengths were all set at 100 feet due to the Indiana Design Manual. This is the other intersection at the easternmost part of the site. This is only a stop-controlled intersection. The turning radii is also 125 feet minimum due to the 45 miles per hour road. And the deceleration is like this, again, 385 feet due to the speed limit. The storage length on this is 75 feet due to the medium-ish volumes on these turning movements, and the taper is again 100 feet. Additionally, the parking lot has been designed. This will be around a theoretical warehouse structure, which is that box that you can see there. Again, annotations have all disappeared. You can see that the spots at the front of the site, I'm at the north end of the site, there are 58 spaces with 3 handicap accessible spaces and with 1 being a van space. And at the back of the lot, you can see 4 storage spots for WB67s and additionally 2 loading bays at the back of the warehouse facility. For future work, I'm going to work on the CAD glitches and see if I can get my annotations and vertical profile to exist again. I'm also going to finalize the construction cost estimate now that I have more accurate numbers on pavement and cut and fill, and I will also be responding to any design comments. Thank you. I would like to pass it to Chris May, our water resources.
Hi everyone, this is Chris for water resources.
Yes.
I want to talk about my scope of work first. It's the overview of the BMP. Second is the cross section of the BMP. It's like mostly about the detail design of the BMPs. Second is the connection of the BMP. And fourth one is the actual assignment of visualizes pre-treatment of BMP, and then the drawing of them. And also make sure that it's all obey the location and local regulations and meet the requirements. And here's my location of BMP. As we can see, the dry pond is at the lowest point, and I also use the vegetative wells to make sure that all the water goes through the BMP and then eventually get to the dry pond. And here's my design methodology. According to the Indiana Stormwater Management Manual and the U.S. Environmental Protection Agency and Minnesota Stormwater Management Manual, and also the Upper County regulation, like with that method, they provide, I can get the size, the slope, and vegetation of the dry gutters. And here's my vegetative wells. Use that method, like to get the 3 months intensity, like use delta depth, like which is the runoff, to divide by the delta time to get the intensity for 3 months. For the water, water quality volume. Sorry, for the water quality control system. And this one is for the site vegetative wells. Also like the CNAs from the last year, and to use the intensity to get the Q real, which is we need that. Like we need to be bigger than that. And then also I have the velocity and the bottom width, the slope, and the cross area, and the wetted parameter. To get the R is like the cross section divided by the wetted perimeter, which is P, and with the kind of adjust the top length and the depth and the bottom width to make sure the Q bigger than the Q real. But I guess I need to kind of adjust a little bit about the top length and bottom width because it's much more bigger than the Q real. But it actually meet the requirement. Second one is the row vegetative wells. This one, it's not just work for the water quality system, also need to work for the flow control system. So, so the second one, the first one is just the same way like the last page, but the second one is use the 6.45, which is from the Upper County regulations. It's like 100 years runoff, so that I can get the intensity for work for the flow control. So with kind of adjust a little bit about the size. So as we can see, also the QS meet the requirement. And right now we go to the tension one. This one is for the preparation for the electrical routing to get the storage and outflow, and kind of adjust a little bit about the length and width. And then we go to electrical routing. The red one is because I did a modified by the TR55, and the red one is like, at this part, the line is kind of straight, so we use the equation to modify it to get this, to get those numbers, and then the number below to the red one is like, use hand to like find a point, and then that's like the process of routing, and eventually we can get like a graph looks like that. It's not really beautiful, but it shows that eventually the outflow is lower than the required ratio, which is proof that the design is good. But also, like I think I need to still adjust a little bit the top length and bottom width to like save some money, because the queue it's kind of too big than required. And here's my future work. I need to do some detailed design of the rain garden and tree box, and also do some drawing of the some drawings, not just cross section, but I will do that at the next presentation. And also the pre-treatment design, also eventually the cost estimate. And with that, I'll give it to our environment engineer, Alexa.
Thank you, Chris. Okay, as he said, I'm Elizabeth Walker. I'm one of the environmental engineers for CEE. Just a quick overview of my scope of work. I am to design a wastewater treatment facility to treat 1 million gallons of water per day. I have already determined the biological treatment alternative, which is to be activated sludge. I have to continue designing the elements of the treatment train, which I will explain in a moment, and make sure all of the effluent meets the requirements of IDEM and NPDES, the Indiana Department of Environmental Management, and the National Pollutant Discharge Elimination System. So this is a look at a typical treatment train. We're starting with pre-treatment. Bar rack is to get really the big pieces out, big trash. Grid chamber is to anything that couldn't be physically manually removed, make that small enough that it will continue flowing with the water, and then it can go to the primary settling and fall out using gravity. Our secondary treatment is the heart of the treatment. It's the biological treatment. That's our activated sludge, as I mentioned before. Then we're going to have secondary settling just to take care of any residuals left by the biological treatment, tertiary water treatment if necessary, and then discharge. So my first element that I have designed is the partial flume. I have, as you can see, my flows, 1 million gallons of water per day as provided by the scope. I went ahead and translated that into metric system because metric system is superior. And making sure I have every different iteration of that cubic meters per day, per hour, per second, everything I might need. The first step is to choose the throat width, which is the smallest part where the water goes through in the channel. And I used the table here, as you see on the bottom, using the flow rate to select the throat width. Then I'm going to be using the partial flume equation, and the target here is to find the depth of water, which was determined to be 0.15 meters. Okay. The next element is the bar rack. There's a lot of little calculations here. The number of bars, the number of spaces between the bars, the area between them that's effectively open. And the target of all this is to find how fast is the water going between the bars, the velocity through, which was determined to be 0.2 meters per second. And then we'll also have redundancies. We need to make sure that this is still going to be operational even if it's clogged up by trash or garbage that is accumulated at 50%. The head loss through the bar rack also is important and limited. It can only be 150 millimeters or about 6 inches, and we need to make sure that we're falling within that range. If not, the bars will need to be regularly cleaned manually. Next up, I have my grit chamber. The detention time is 8 minutes. I have the volume. I went ahead and used the table here, table 20-12, to assume some depth and width of the grit chamber and using those values to determine the length of the chamber, all of which ties back into the detention time, which is how we can adjust it. We need to be double checking these using the ratios as seen in the table to make sure that the ratio of width to depth and length to width are falling within the correct ranges. Next up, I had to find the velocity along the bottom of the grit chamber. We need to make sure that the water is not going too fast and picking the grit back up as it goes through, because the idea is to remove the grit from the water, so we want it to fall to the bottom so it can be removed. And then we also need to make sure that in the worst case scenario, if we have a really high loading of grit, that our equipment is going to be able to handle that without failing. In the future, I'm going to be working on finalizing these designs. There are other pre-treatment elements that also need to be developed. I'm going to be working on starting on the secondary treatment, the activated sludge, and continuing working on CAD drawings. With that, I will give it to Caitlin.
Hello everyone and good morning. I'm a Construction Consultants Environmental 2 engineer. So just to give a refresher on my scope of work, I was tasked with designing a drinking water treatment facility to treat 1 million gallons of water per day. I had to determine the location of the treatment facility and fire protection on site. I had to determine the size of the treatment facility and each corresponding treatment unit. I had to select the fire protection and design according to local and national standard codes once my water source was chosen last semester. Another refresher just on the location of my water treatment facility and where my fire protection will be located on the property. And then once again, another refresher on the selected drinking water treatment train. This is a typical drinking water treatment train when it comes to groundwater, and this is what I will be using. To go further in depth into each component of that, we will start off with my intake structure, which is a submerged pump and a well system. The water source that I will be using is the St. Joseph Aquifer, which is an unconsolidated aquifer. The pump type typical for these situations are vertical turbine pumps, which will be submerged. And it will also include a well screen to filter out any solids being retained. The estimated static water level based on Elkhart County's water reports ranged between 0 to 90 feet throughout the entire area, but in most areas it ranged from 5 to 50 feet. So from this I was able to estimate a 25-foot static water level, and the total depth of my wells will be 85 feet. This is based off of the calculated flow rate of 700 gallons per minute, which gives the ability to intake 1,008,000 gallons of water per day to reach that 1 million average. Moving on to the well design, the well type that will be used are gravel-packed wells, and there will be 3 of them in order to comply with the redundancy and demand requirements. They will be flowing in parallel in order to provide consistent flow, and based on Elkhart County's regulations and just water requirement regulations, they need to be spaced 75 meters apart. Moving on to the pre-oxidation stage of my treatment train, the required detention time for this stage is around 45 minutes. With this and the required flow rate, the flow rate for this is going to be about 2.65 meters cubed per minute, which gives us a volume needed to hold 31,506 gallons of water. So based on the chosen dimensions, the total capacity of these units will be 32,387 gallons. And based on redundancy requirements, we need to have at least 2 of each of these units just in case one goes out. When you have 2 units, you need to make sure that each one is able to support the full capacity needed to carry If you have more than 2, then it can be split up in some sort of way, but for this one, each one is going to have the same dimensions. Same thing for sedimentation tank. This one requires a detention time of about 4 hours. The flow rate for this is 159 meters cubed per hour, which gives us a volume needed of holding about 168,000 gallons. The total capacity based on dimensions chosen with a diameter of 48 feet and a depth of clarification of 13 feet will be about 175,974 gallons with two units used again, one in use, one on standby in case one breaks or just something goes wrong. Then we have the rapid sand filter. The required detention time for this is 3 hours with a flow rate of 159 meters cubed per hour, giving us a volume needed of about 126,000 gallons. The design volume for this one will be about 500 meters cubed, which is roughly like over 130,000 gallons, and 2 units will be used for this. Dimensions are still being chosen. Next is the lime soda softening treatment. The required detention time is 2 hours for this, and that along with the flow rate gives us a volume needed of about 84,016 gallons. For this part of the treatment, we are going to use 3 units, so 2 will be in use at all times while 1 is on standby. When it comes to groundwater, the water tends to be very hard, so this is a very important part of the treatment process for this specific water source. Moving on to the storage, which is kind of the last part of the treatment train. The design capacity determined and needed for these storage tanks is about 750,000 gallons. So 3 tanks will be used. Based on the dimensions chosen, each tank has a capacity of 264,383 gallons, leaving a total tank capacity of 793,149 gallons, with all 3 in use. From there, we also have the fire protection, which will be on site. 2 fire hydrants will be present on the property, which was shown previously in the location slide that I had. The fire hydrants chosen are the East Jordan Ironworks 5BR250 fire hydrants, and this was chosen based on Elkhart County's fire protection requirements. Fire protection and fire hydrants need to be within 600 feet of any buildings on a property line. So 1 will be located near the water treatment facility, and then 1 will be located near the building and parking lot and wastewater treatment facility, because it can reach all required areas. And then each fire hydrant requires a flow of at least 500 gallons per minute with a residual pressure no lower than 20 psi, which these calculations still need to be completed. My future work includes the selection of well and distribution pumps, specifically final determination of chemical treatments and dosages, water distribution to fire protection and pressure calculations, the finalization of my schematic drawings and dimensions, and then my final cost analysis. And I will hand things back over to our project manager, Lily.
Thank you, everybody, for coming today, and we would now like to open up for any questions you may have. Yes. Yes, you.
Let's start with Caitlin in here. Simple questions for you, Caitlin. I'm not familiar with that reference, Frank 2025, so can you tell me who?
Those are my drawings. Yeah, so I just use my last name. I need to figure out how, I need to reference that, add that into my reference doc, but all of those are referring to my own drawings, yes. I just wanted to make sure that they had captions on them so everybody kind of knew what they were.
Thank you. I did not hear anything about disinfection, and so are you including any disinfection in the process, or did I miss that?
Yes, I will be. This has not been determined yet. It's still something that I need to analyze.
And why did you decide to use rapid sand filtration versus like pressurized filtration tanks for groundwater treatment?
I was just looking up different examples because Elkhart County specifically uses all groundwater as their source, so I was looking up what their typical systems were and kind of tried to follow along with what they already have and what works for them.
Okay, thank you. Elizabeth, I think next in line, environmental in here. Well, let's go back to the grid chamber. So lots of your design things. And so you, actually if you want to go to the previous slide, yep, on this table, you decided to start with a detention time of 8 minutes 480 seconds, and if you look at their typical range values, and I see it from 120 to 300, so why you decided to not follow the guidelines?
Yes, so actually I did start with an assumption of 3 minutes, and with that time, I was not able to get those width and depth and length and width ratios within the correct range. So these are typical designs, these aren't the mandated times that must be chosen. I was able to go back and kind of fiddle around with it and make it work. Because we have such a low volume of water going through here, compared to like a typical like municipal facility, the length of our chamber is really short. So the water is going to need more time to stay inside of there for the grit to fall down to the bottom properly. So it's going to be in there for a bit longer than a different facility.
Can you
would be.
flip to the previous slide also for the head loss propagate? Why do you have negative signs in front of the numbers?
Because the water is falling down below, it's not rising up, it's going down.
It's a head loss calculation.
Yes.
Right?
Exactly.
Okay, it should be, and actually you mentioned down there, it's just you got to be somewhere between 0 and 150, up to 6 inches.
150 is the maximum that it
Correct.
could be.
So you don't want to exceed 150, but it's a head loss in the system, so why it's negative in this case? Okay, I'll leave it there.
Thank you.
Take a look at it in there. Chris, I know you had lots of numbers I could not keep up, so I want to pick on one of them. So if you're going to go to the vegetated swale table,
This one?
no, the long one with, yep, this one in here. Now, before, actually, even on the next slides, I was impressed with how accurate your numbers are. Like the flow rates has like, what, 12 significant figures in there? So maybe like, so how accurate when you do these calculations you expect or you think? Can I call it like exact numbers or they are estimates? I mean, this is general and maybe applicable to everyone in case in here. So why do you carry so many significant or decimals, let's say, in your calculations?
I think for this one, like the time and depth, like it's all like go through a calculations. So I think it's accurate number. It's not just estimate.
It's accurate.
Yeah.
So if you go to the next slide,
What are the units?
yeah, that's it. Okay, exactly.
Which
That's
one?
go to yep. Stay here. So you tell me Q equals 6.646828513. That's accurate.
I think I should like do less number.
I could guess it's CFS because up there on the first row it says CFS cubic feet per second in there, but okay. So let's go back to the table, the vegetated swale table. Can you explain to me, because I could not follow up on here, tell me, I don't understand it, so you have to explain it to me. What am I looking at?
Like the intensity or depth?
All of it, so I don't, so this is a vegetated swale, so to me it's an open channel. That's how I think about it.
The first list is the percentage of time. The second one is the percentage of the depth.
Of
And-
what? Percentage of time of what?
Of 24 hours. Because it's 24 hours.
And so when you, 24 hours, this is a percent of the time,
Yeah.
the depth, will be, okay, now I'm beginning to understand, yeah. So in this case, your maximum depth will be 1.51 what units? Feet,
Inch.
inches.
Yeah.
So that's the depth of the flow,
Mm-hmm.
1.5 inches.
I guess it's run out.
And what's the intensity in this case?
The intensity is it's used like for example, use this one, subtract this one to divide by this one, subtract this one to get intensity.
What does it mean, intensity in this regard? I know if there is a rainfall intensity, I understand that. But if it's a flow in a vegetated swale, so what does the intensity mean in this case?
Like, what's the intensity? Like, like how strong it is.
Maybe you want to explain that in your report, so I'll read it in the next one in there. So,
Okay.
and make your numbers maybe, they are
Yeah, I think
estimates, like we deal
I
with
should make-
hydrology, rainfall records from the last 70 years or so. So they are not exact or deterministic, so that's what I think.
But that's the depth of rain, right? That's not the depth of water in the vegetated swale. That's the depth
Yeah,
of rain.
yeah.
Okay,
Yeah.
that makes a difference. Yeah.
And okay. So, like you showed your detention pond, your level pool routing, right? And you have a vegetated swale table here that's about the rainfall, but like how big is your detention pond and how big did your vegetated swale end up being? Do you have any?
How big the detention pond?
Yeah.
Like,
Oh,
very
okay.
length.
Length and width, okay.
Yeah.
How about
the depth is 3 feet.
That's the maximum depth.
Yeah.
I mean, through the routing process, it reached 3 feet exactly?
Yeah.
Okay. And then like, how about your vegetated swale? What's the dimensions or how wide is it? And
Vegetated swales. For the site, like
okay,
there's a bottom width and the top
Okay.
width, and then depth.
so it's in there.
I think
Okay.
I should do more units, but it's right there.
I was looking at all the other numbers, I didn't notice those.
Is there any questions?
No, I was just wondering what the result was.
Maybe just a word of advice in there. Actually, goes to almost this entire team in here. When you give this type of presentation, we honestly not interested in the detailed calculations, I would say, for the audience. If you just summarized, here is my, for example, grid chamber design, and here are the dimensions. This is the same with like the swale, the detention pond, and many of those, rather than showing us all these like tables and details and spreadsheets of the calculations, which is we cannot follow as you scroll through the slides.
Okay.
You can mention the process and the concepts that are used, right? And then maybe like show a cross-section of the swale.
For example, for the level routing,
Yeah.
I think that's pretty hard to do the sample calculation.
Yeah, you don't even have to do that. You can just say level pool routing. And then, yeah.
All right, I had a question there, I saw that hand over.
I did. I think for Caitlin, you talked about having one of your units and then having another one as a backup.
Yes.
So how does that work? Once-
So this is based on like the redundancy requirements, just based on like the US EPA and water management resources. You need to always have a backup when there's only a certain amount of units in case one goes out. So you have another one on standby in order to take its place, since the system needs to continue running, like it has a purpose. So you always need to make sure that there's an extra in case the first one goes out.
Okay, but my question is how, do you leave one just sitting there forever, let it, 10 years from now, something happens, you know that one's never been used, it's gonna work? Or do you, does this?
I'm sure you would just
You
take
rotate
turns.
this in and out?
I would assume that you would rotate them out. That's something that I haven't necessarily explored. I was just specifically looking at the redundancy requirements and trying to choose the amount of units that I have based on that. But I'm sure that in order to, I mean, it's like the same thing as a car, like, you can't let it sit for 10 years or else it's not gonna work when you try to run it again. So I would assume that the facility would probably try to rotate them out and make sure that they were both running consistently.
I would think so also. It might be something you want to point out in your report.
Thank you.
Are there any further questions at this time?